Welcome, traveler. How did the world around us form, and how did it evolve into the Earth we know today? The history of our planet begins 4.6 billion years ago. Initially, Earth was a molten sphere, constantly bombarded by other celestial bodies. A giant impact with a Mars-sized object named Theia is theorized to have led to the formation of our moon. Over time, the Earth cooled, allowing a solid crust to form and liquid water to exist on its surface. At that time, everything looked very different from what we know now. Yet, over billions of years, Earth would become hospitable enough for life to emerge and for humans to permanently inhabit it. Dear traveler, welcome. Across 4 videos, we will explore the heart of our planet, from its birth to its evolution. You are now on the 3rd episode. Previously, we explored the journey from the formation of the Earth to 500 million years before present. Now, we continue this journey to 250 million years before present. Every planet has a history. This is the story of Earth. The Earth initially presented a barren landscape. Lava flows from volcanoes rolled down their sides. Volcanic activity was rampant in Earth's early history, releasing gases from the interior that helped create the early atmosphere. Today, these volcanoes are dormant, though they still crackle and slowly solidify. Pools of yellow, blue, and gray mud bubble. Heat from the Earth's core bursts through the surface in thick, swelling blisters. When the first volcanoes appeared, they erupted violently. These eruptions eventually cooled, forming massive mountains of ash and lava. Over the years, these rocks eroded under the influence of wind and rain, turning into mud and clay. Debris carried by streams eventually reached the seas, accumulating to form shale and sandstone. Meanwhile, the continents, constantly moving, collided and dragged surrounding sediments, compressing them into new mountain ranges. This continental drift, proposed by Alfred Wegener, explains how continents like Pangaea once joined and later fragmented. The movement of continents is driven by plate tectonics, where Earth's lithosphere is divided into plates floating on the semi-fluid mantle. These plate collisions result in mountain building, volcanic activity, and earthquakes, constantly reshaping our planet. Geological cycles advanced. Volcanoes erupted, then became dormant, and life proliferated in the seabed. On land, however, the surface remained sterile. 4 major continents emerged: Laurentina, Baltica, Siberia, and Gondwana. These landmasses continued drifting. On the opposite side of Laurentina, the edge of Gondwana began to fragment into smaller continents. The first of these was Avalonia. Its movement shrank the Iapetus Ocean and opened the Reich Ocean, marking the beginning of the Caledonian orogeny. This significant mountain-building event occurred from 490 to 390 million years ago, caused by the collision of Laurentia, Baltica, and Avalonia. By 485 million years ago, primitive plants, born from the union of algae and fungi, emerged onto rocks, stepping out of the water. These plants decorated sandy shores and rocky edges with green carpets. Away from the humid spray, they would dry out and die, as they lacked specialized tissues for water transport. The first land colonizers developed the ability to survive drying out, returning to life when the rain came. Other plants developed an impermeable cuticle layer to reduce water loss. For now, plants remained simple, with primitive vascular tissues and no leaves. Their reproduction remained closely tied to water. Mosses were among the first plants to colonize dry land. They remained close to the ground and only grew near moist areas. Lacking roots, mosses relied on stomata for gas exchange and grew tightly together for vertical support. Mosses acted like sponges, absorbing water and releasing spores to reproduce. alternating between sexual and asexual cycles. Sexual reproduction was evolutionarily significant, requiring gametes to meet and combine in a liquid environment. Eggs attached atop stalks while sperm swam through water to fertilize them. Plants used photosynthesis to create their organic matter, drawing carbon dioxide from the atmosphere and releasing oxygen. The spread of plants on land marked the second major oxygen increase in Earth's history, following the Great Oxidation Event. The Great Oxidation Event, driven by ancient cyanobacteria, first introduced significant oxygen into the atmosphere billions of years prior. Soil began to form as plants colonized the surface, died, and decayed. Their remains created humus, providing fertile grounds for fungi, animals, and more complex plants. Mosses and liverworts spread, forming green mats across the land from the coasts inward. At this time, the land was barren but covered in moss and simple plants. The temperature hovered around 30 degrees Celsius. The ozone layer thickened, but still partially allowed ultraviolet rays to reach the surface, making underwater habitats safer for life. Gondwana stretched from equatorial latitudes to the South Pole, partially covered by shallow seas. Its proximity to the pole gradually triggered a cooling trend, initiating glacial formations. Later, vascular plants like Cooksonia and lycopods would dominate, developing roots, stems, and leaves to colonize drier habitats. The evolution continued with seed plants and flowering plants, further diversifying life and shaping the ecosystems we recognize today. This incredible journey through Earth's ancient past reveals the profound transformations that shaped our world and paved the way for the diverse life we see today. Around 460 million years ago, before significant cooling began, life thrived in Earth's vast oceans, which covered most of the planet. Oxygen levels in the atmosphere were only 2% of what they are today. Yet this era marked the Great Ordovician biodiversification event. Around 490 million years ago, Earth's atmosphere was rich in carbon dioxide, creating a greenhouse effect that kept temperatures high. Ocean temperatures reached a scorching 45 degrees Celsius, severely limiting the availability of dissolved oxygen for marine life. However, photosynthesis played a crucial role, helping to absorb carbon dioxide and stabilize these extreme environmental conditions. 30 million years later, as the continents cooled, a dramatic surge in biodiversity transformed the oceans. Marine genera quadrupled, and the oceans became teeming with an incredible array of diverse life forms. The development of plankton enabled a wide range of benthic fauna, including cephalopods, crinoids, and brachiopods, which secreted carbonate shells. Coral reefs began to develop, soft-bodied organisms spread, and mollusks proliferated across the ocean floor. Trilobites, some reaching an impressive 60 centimeters long, foraged the seafloor for plankton, algae, and detritus. They shared these vibrant waters with primitive fish like astraspis, small armored vertebrates that were ancestors to future vertebrates. The Orthoceras, a formidable 6-meter-long predator, dominated the ocean with its distinctive conical, gas-filled shell for buoyancy. Despite its fearsome presence, it faced no threat from the giant Eurypterid, or sea scorpion, the largest arthropod of its time. Growing up to 2 meters and weighing 130 kilograms, this creature preyed on invertebrates, mollusks, and primitive fish with its sharp pincers and needle-like tail. Coral reefs thrived, slowly colonizing the ocean floor and forming complex ecosystems. These corals, small plant-like animals, formed intricate skeletal structures, creating shelters for countless marine species. They harbored symbiotic microalgae for photosynthesis, meeting most of their nutritional needs while filtering plankton with their tentacles. However, this vibrant marine life faced its first major extinction event. A nearby star went supernova, releasing a massive gamma-ray burst that reached Earth within 10 seconds. This burst delivered energy equivalent to 10 suns, destroying atmospheric molecules and damaging the ozone layer by 30%. The planet's surface was exposed to devastating ultraviolet radiation, initiating a catastrophic chain of events. Plankton, the very base of the food chain, died off en masse, leading to a cascade of starvation. Many corals perished, triggering a widespread collapse of the intricate marine ecosystems they supported. Within months, a toxic nitrogen dioxide-rich atmosphere formed. An extensive glaciation plunged temperatures to a frigid 12 degrees Celsius. Only the most adaptable species managed to survive this unprecedented environmental catastrophe. Trilobites retreated to colder, deeper waters, while Astraspis evolved specialized gill structures for nutrient absorption in the changed environment. Eurypterids, the sea scorpions, also adapted to the new conditions, gaining resilience and continuing their predatory existence. Coral reefs collapsed, sea levels dropped dramatically, and new habitats emerged for the surviving organisms. Millions of years after the first plants had colonized land, the first animals ventured out of the water. Segmented organisms, ancestors of millipedes, developed chitin exoskeletons and a tracheal respiratory system to survive on land. Adapting to terrestrial life required entirely new reproductive strategies, as gametes could no longer move freely in water. Meanwhile, plants diversified, developing vascular tissues to transport water and nutrients efficiently. Lycopods, horsetails, and ferns emerged 420 million years ago, growing tall and forming dense forests. Some of these ancient trees reached an impressive 30 meters in height, transforming the very landscapes of Earth. These burgeoning forests created new ecological niches for animals, driving further evolutionary adaptation and shaping the future of life on our planet. By 250 million years ago, Earth's landmasses had converged, forming the colossal supercontinent known as Pangaea. This immense landmass extended significantly from north to south, positioned centrally along the equator. The interior regions of Pangaea were characterized by extreme heat and arid conditions, a stark contrast to the more temperate coastal zones. Coastal areas, however, benefited from oceanic influences, maintaining warm and humid climates that fostered diverse ecosystems. The formation of Pangaea triggered significant global changes, including dramatic shifts in sea levels and the emergence of new ocean currents. These geological transformations led to profound climate changes across the entire planet. Within the vast interior, expansive deserts and saline marshes became prominent features of the landscape. Conversely, along the coasts, rivers, lakes, and wetlands provided crucial habitats, supporting a rich array of life. During this pivotal period, tetrapods achieved full adaptation to terrestrial life, marking a significant evolutionary milestone. Species like Ichthyostega and Acanthostega were no longer bound to aquatic environments, venturing onto moist shorelines to hunt and explore new territories. Simultaneously, the first truly terrestrial insects made their appearance, revolutionizing land-based ecosystems. Equipped with segmented bodies and an efficient tracheal system, these insects could navigate land, breathe atmospheric air, and endure dry conditions. The plant kingdom also underwent rapid and dramatic evolution during Pangaea's reign. Ferns, horsetails, and lycopods grew to colossal sizes, forming dense, ancient forests. These thriving forests were particularly prevalent in Pangaea's humid coastal and swampy regions, creating lush green landscapes. Beyond providing shelter for terrestrial life, these enormous plants played a crucial role in increasing atmospheric oxygen levels. Through the process of photosynthesis, oxygen concentrations in the atmosphere rose significantly, enabling the development of more complex life forms. Pangaea's terrestrial ecosystems evolved into intricate webs of predator-prey relationships. Large amphibians and early reptiles became formidable hunters, preying on insects and smaller tetrapods. Plants served as both vital food sources and essential shelter, structuring these ecosystems. This interplay created increasingly complex food chains, fostering a rich biodiversity. However, around 252 million years ago, the Permian period concluded with the most devastating mass extinction in Earth's history. Massive volcanic eruptions within the supercontinent's interior unleashed colossal lava flows. These eruptions released vast quantities of carbon dioxide and sulfur dioxide into the atmosphere. This atmospheric deluge triggered rapid global warming, widespread ocean acidification, and severe depletion of the ozone layer. Marine life bore the brunt of this catastrophe, with trilobites, many brachiopods, and numerous coral species vanishing forever. On land, while some amphibians and insects managed to survive, the terrestrial ecosystems were profoundly disrupted and altered. The Permian extinction reshaped life on Earth, paving the way for new evolutionary paths and the eventual rise of the dinosaurs. This monumental event serves as a powerful reminder of Earth's dynamic history and the profound impact of geological forces on life. Following the extinction, the Earth slowly recovered. Sea levels rose, Pangaea's climate stabilized, and ecosystems began to rebuild. Survivors adapted to new environments. Early reptiles diversified, with some emerging as terrestrial apex predators. This recovery laid the foundation for the rise of dinosaurs in the next era, the Triassic period, rebuilding life. After the Permian extinction, life slowly recovered during the Triassic period, around 252 to 201 million years ago. Pangaea still existed as a massive supercontinent, but its interior regions were arid and desert-like, while coastal areas remained more humid. This harsh climate favored species that could survive in extreme conditions. Reptiles became dominant on land. Early archosaurs, the ancestors of crocodiles and dinosaurs, began to diversify. Some reptiles adapted to walking upright, improving their mobility and hunting efficiency. Amphibians, though still present, were now largely restricted to wetlands and rivers. Insects continued to diversify, including early beetles and flies, which spread across the dry and wet regions alike. Plant life also adapted. Gymnosperms, including conifers and cycads, dominated forests, replacing some of the ferns and lycopods from earlier periods. The rise of dinosaurs. By the late Triassic, the first true dinosaurs appeared. Small, agile, and bipedal, these early dinosaurs exploited niches left vacant after the extinction. Predatory theropods hunted insects and small vertebrates, while herbivorous sauropodomorphs fed on ferns and early gymnosperms. The evolutionary advantage of dinosaurs lay in their posture, respiratory efficiency, and rapid growth, which allowed them to outcompete many other reptiles. Over millions of years, they diversified into countless species, laying the foundation for the Mesozoic era, often called the Age of Dinosaurs, the breakup of Pangaea. During the late Triassic and into the Jurassic period, tectonic forces began to fracture Pangaea. Rifting created separate land masses, Laurasia in the north and Gondwana in the south. This breakup affected ocean currents, climate patterns, and species distribution. Coastal regions became wetter, deserts shrank, and new shallow seas formed, creating abundant marine habitats. Dinosaurs thrived in these newly isolated ecosystems. On Gondwana, massive sauropods evolved to feed on tall gymnosperm forests, while on Laurasia, diverse theropods and early ornithischians dominated different habitats. Then, 66 million years ago, a cataclysm struck. A massive asteroid slammed into what is now Mexico. Blazing fires, choking dust clouds, and sudden climate chaos wiped out nearly all dinosaurs and countless other species. Yet from this devastation, new life began to rise. Small mammals, once hidden, ventured into open niches. They evolved into herbivores, hunters, and even aquatic forms. Birds, the resilient descendants of dinosaurs, survived and flourished in the New World, the age of mammals. With the giants gone, mammals expanded across every ecosystem. Over millions of years, they grew in size and diversity. Elephants wandered the forests. Whales claimed the oceans. Carnivores prowled forests and plains. Grasslands spread, feeding vast herds of grazers. By the Miocene, the Earth resembled the world we know today. From the tiniest microbes to the giants of the past, life's journey unfolds in all its glory, reminding us that we are part of a story that has been going on for millions of years, and that the adventure still continues. We've reached the end of the documentary about what the world was like 500 million years ago. Would you like to see what the world was like 250 million years ago? Let me know in the comments. See you soon. If you enjoyed this journey through time, please like this video and subscribe to our channel for more stories about our amazing planet. Thanks for watching.